Hello, everybody. My name is George Whiteside, and I'm speaking today with my coworker, Benjamin Wong. We're going to be talking to you today about a retrospective on our experience supporting a debugger for bare metal high-performance computing architectures. So first, we'd like to talk about some broader context, who we are. We work for Reservoir Labs. Our business is to provide tools and tool chains for novel architectures. The past couple of years, we've been working on a couple of different high-performance computing architectures. And we're excited to talk with you today because we anticipate a large proliferation of new and specialized architectures. And debuggers provide enormous value to developers on these architectures. So we hope that some of our experience providing debuggers in our work for the last couple of years will be helpful going forward.
Yeah, so to get a little bit more into the specifics of our architecture, as George said, we're working on high-performance chips. There's no operating system, so we're developing a debugger for bare metal attached devices. And we have a really high number of threads. We're working with a number of threads that's in the tens of thousands. And these chips also have a lot of different kinds of memory, a very heterogeneous memory space, and that's sort of unevenly distributed across the chip and has different advantages, disadvantages to the different pieces of memory. Next slide. Maybe that prompts the question, why would we choose LLDB? Well, first of all, the tool chain, the rest of the tool chain was already being developed in LLVM. The compiler was developed in LLVM with great success. So that already predisposed us to pick LLDB because it's also part of the LLVM umbrella project. But additionally, LLDB provides a full-featured command line debugger that's backed up by a modern retargetable code base. And so the time to get a debugger up and running on our chip is pretty low, especially considering you're looking at the entire development team for these debuggers for several high-performance chips. And additionally, another big advantage for us was that our users are super users. They really know the architecture. They know exactly how the architecture works, and because of that, they really want to take our tools and extend them. So Python scripting is a huge boon for our users. It allows them to really get the best out of our tools.
So, however, once we started getting into this work, we encountered some difficulties. And we noticed a recurring theme with these as we kept working on them, which is LLDB assumes that its targets have a POSIX environment or are operating in a POSIX environment. That's very restrictive for our use case. And we like to take a look at 3 specific examples, starting with stepping. So our architectures do not have an operating system. We don't have a full complement of ptrace system calls to manipulate the process being debugged. And the hardware support for stepping processes and programs is not consistent across architectures. So what we've done to address this in the current debugger is we've disabled certain run modes. So, for example, one architecture works best if we're only running one thread at a time. Another architecture can only run all threads. There's no way to run only one thread at a time. And disabling these was pretty straightforward. However, this caused some issues with some of the thread plans that are provided by LLDB to provide some convenience in handling to the users. Where these thread plans would assume that all the run modes are available or would default to certain run modes that were unavailable for our architectures. We ended up having to work around this and even disable some of the thread plans. The second problem that we encountered is that LLDB expects a virtual memory space from the operating system. So this is a large homogeneous address space that a process gets when it's started in a modern operating system. However, our architectures don't have this. They have a more complex and differentiated memory. Specifically, thread local memory has been an issue for us. So we've had to disable memory caching, which is a really nifty feature of the debugger that we're sorry to miss. And we've had to add additional hardware context whenever we execute a memory transaction. For example, this below code is the process read memory function call with the additional hardware context of the thread ID there in bold. This change was a little onerous as it required the API for read memory to be changed all up and down the call stack from process to process plugin to server client to server to native process. It was relatively straightforward once we figured it out, but I think it highlights our message that these POSIX-like assumptions are restrictive for us.
Yeah, and the final problem that we encountered was related to the threading model. So LLDB expects a POSIX thread model, which is represented by the native process thread and register classes in the backend. And the issue is that our hardware just doesn't really fit into that hierarchy very well. We have a very large number of threads that are organized into a more complicated architectural hierarchy. Probably the best example of this that's publicly available are warps and threads in a GPU. And that kind of came down to a question for us of how do we create a usable debugging model while taking advantage of the LLVM infrastructure and slotting into this process thread register hierarchy. Next slide. So our solution for this was twofold, really. First, we basically restricted the vision of the chip to a small slice at a time. So the user can only really look at 16 threads at a time. And these slices are chop up the chip into architecturally relevant slices. And we allow the user to select this slice dynamically so that at one time, they can only really see a small portion of the chip, but if they desire, they can look across the entire chip by changing what slice they're looking at. Additionally, we had to add support for this hierarchy, especially within the backend. So we needed to expose hierarchy-specific commands to the user that allow them to operate across slices, depending, sort of based on how these slices are connected together in the hierarchy, and also kind of provide add additional classes and complexity to the backend to get around the existing hierarchy that's pretty deeply embedded.
So we've talked a little bit about the problems we've encountered and the solutions that we've come up with. And the next question that we're asking is how we can contribute some of our work back to the project. We haven't upstreamed anything yet. It's been difficult to untangle our work from the private architectures that we work on. And it's difficult and intimidating as new contributors to change something like the POSIX environment because it does seem to be so core to the existing code base. We are thinking about ways to extract and upstream parts of our work, and we would love suggestions from current contributors about the best way to do that. Finally, to wrap things up, we would just like to say that we plan to use LLDB in future projects. It's a very great tool, and we appreciate all of the work that's been done by the current contributors. So thank you very much.